Okay, I wanted to make a little video about, um, about peak hole detectors. And, some years ago I built this circuit as part of another project. And, and I kind of fucked up the wiring a little bit. I had to repair it, because this actually shouldn't be wired this way. This shouldn't be going back to the positive terminal. It should be going to the negative feedback, and this wire here shouldn't exist. Anyway, this is what it looks like today and what it's supposed to look like back then. Um, and um, and I want to say too before I forget later, in a previous video, God damn Microsoft. In a previous video, I talked about how, I had this zero crossing detector here, right? With a 741 op amp, and I have the positive rail tied to 5 volts, and the negative rail tied to minus 15 volts, because that was the only negative power supply I had handy on this. So it's asymmetric, but it still works perfectly. In fact, I still got that circuit running in the oscilloscope over there. But and it's part of a power supply board is what it was, so that was meant to send, zero crossing pulses out to a CPU. But yeah, the whole point was is to, and I probably should have actually used, more like, 6 or 7 volts, which, for the positive supply, but again, then I would have to have a dedicated power supply for it. But, but still, it puts out a usable enough signal. Um, but the point is that, I have an asymmetric supply, and like I pointed out in the video, you don't need you don't really need the power supplies to be the same, always. Most of the time you want to do that, but you don't have to have it that way. And this is one circuit, peak hole detector is one circuit where that could come in advantage because it's a positive peak detector, right? So as a result, its input really doesn't need to go very negative, right? But on the other hand, if you had a more positive supply on this thing, then this capacitor could charge up to a larger voltage with respect to ground. Now you got to pay attention again some of the nonlinearities you might get in an op amp by operating it that way, especially if you start getting really close to one of the supply rails. But if you put like a a minus 5 volt supply on this op amp, which is charging this capacitor, versus like a 25 volt positive supply, on the positive side, and then had a ground in between those two, all right, then you'd essentially be able to charge this capacitor up to, like 22, 23 volts, instead of being limited to like 12 or 13. So you get more range out of it, is the whole point. But, if you're going to be charging capacitors up to that much, you want to, investigate a version of this circuit that will actually equalize the diode voltage, because this diode here will result in a lot of leakage, discharging your capacitor back through the source. But that's one of the good reasons to use a, like a 5 volt minus supply, because it'll never allow it to go much more than that. But it depends on the signal you expect to put in, though. If you are going to have an AC signal coming in, you probably wouldn't want to do that. But if it's just a DC signal, that you're wanting to positive peak detect, yeah, you could do that to get extended range out of your, out of your device. So, and I was going to say, actually I did find, on ESP Guy's site, let's see if I can find it real quick. Here we go. Oh. Okay, that's strange. Oh, I didn't know I had 2 of those. Huh, got 2 of those folders. Okay, let's see. Well, still don't see it. Hold on. Yeah, it was right in front of my nose all the time. It's called AN014. That's not peak detection circuits. And in fact, fuck it, I'm going to rename it. anyway, but yeah, he talks about, well, shit, I stand corrected. Okay, this is, well, I don't know. Yeah, this isn't what I had in my notes. God damn it. Yeah, yeah, this is the article I'm actually looking for. So, yeah, that other one I guess is something else. It's named the same damn thing if you do a Google on it. But anyway, but you can see what the address is here. If you want to go find this. But yeah, like I said, he talks about several peak detection circuits, including one that actually blocks the diode voltage so it equalizes it, because this diode leakage is actually a significant factor in discharging your capacitor. So, because you get a voltage drop of, from the output of the, from the output of the op amp there to your capacitor. So the reverse current that flows through the diode tends to discharge it. So, oh, what is this? Oh, this is something else. Yeah, that's nothing to do with anything. Let's see. Study semiconductors, that's what it is. Okay, but yeah, if you look at a standard peak detector here, this is what you get. Looking at this graph here, you see what the actual output voltage is right here. It's negative 15 volts most of the time. So, people reset it. All right. Now it's charging up. You're seeing what the capacitor is doing here, but you see these spikes. Those are the only time that the output of this op amp is not minus 15 volts. It just pegs it, to the negative supply rail because it acts like a comparator basically. So when this voltage of the plus terminal drops below whatever the voltage across this capacitor is, it just pegs to negative VCC. So, any rate, that's bad because A, it causes your op amp response problems because, there's kind of a recovery time when you saturate an op amp to one of the supply rails. I think it's mostly an input issue, like I said before, but I mean, that's what essentially, you just don't want to do that. You usually don't want to allow it to excursion to the point to where it's, pegging to one of the power rails. Usually that's just kind of a no-no. You want to try to avoid that in op amps. Because it, at the very least, slows your op amp down, when it comes to signal response. And, even if there's not a problem with it, there's still a slew rate issue, right? It still has to slew clear back to the other side, before it can actually respond to your signal in a positive direction. You don't want to doing that. So you like to limit it. And he's got some circuits that actually limit the diode voltage drop, to when that condition happens, when the positive terminal is lower than the negative terminal. In other words, always happens, when it drops down from peak. Because remember, this capacitor stays at that charge, right? So that's what it's kind of comparing it to. So anytime this drops below that capacitor charge, it'll try to peg it negatively. But, some of his circuits actually, that wrong goddamn one. Let me close this. Like this circuit, is supposed to actually do that. It's supposed to keep it, at least one of these diode drops that way. I don't think it does it for the op amp output, but at least keeps the voltage across the capacitor constant, so it doesn't discharge, because that's one of the other drawbacks to it. Is the capacitor will discharge through that diode because it's got like 15 volts. The higher the voltage across this diode, the higher the leakage current's going to be, right? So the faster it'll discharge your capacitor. So again, that's not a good state to leave things in. But the one I built, was an improved version I got out of the Hazen textbook, actually. So it's about a direct copy, except I did the schematic, drew the schematic wrong. But yeah, it, is basically this design here. So, like I showed you. Now, Here you see the same kind of, we're monitoring the voltage on the output terminal, but it never has an excursion more than the input signal. So, it's at least staying within, that limit. It's not swinging to the negative power rail. So that's way better in terms of a response. Although this circuit does use global feedback, so this will slow it down a little bit because there's a propagation delay to an op amp. So that second op amp does in fact slow the frequency response of this down a bit. But on the other hand, it does at least prevent it from going to a negative excursion by using this kind of feedback technique. So, if I reset the thing, you can see the capacitor. This is the input signal, and it starts to charge up and stuff. But you don't see any anomalies like you do on the other one, where it's pegging down to the power rail. In fact, this is what you're seeing, essentially in the output of the op amp. Okay, so in fact, we could probably look at that too. For shits and giggles, what the actual feedback signal. It should be kind of similar, to this, but this is the signal that's actually being fed back to it, which itself does go, to negative excursions, but it also keeps the output limited to the same way, because this thing thinks it's happy-go-lucky. It's basically doing sort of a unity gain thing, but you got to remember, this is not a strictly linear circuit. It's non-linear because for a while it's got to use, when it's starting from 0, it's got to get that, it's got to overcome this diode voltage drop, right? So, it'll receive, like, let's say a 5-volt input, right? And, but this is at 0 input because it's in a reset state. Well, it's going to try to slew its output positive until it can equalize these terminals. So, until it overcomes that diode voltage drop, it's actually sort of non-linear. That's what they call non-linear. Even though it's actually linear, it's just at a really high gain. So it's at an open loop gain. It'll slew up really quickly to that diode voltage drop, and then it'll try charging up that capacitor. So that capacitor's got to charge up, and as it charges up, that voltage is being fed back through this feedback circuit, and still it happens quickly enough. But again, the size of your capacitor and the current capacity op amp are going to be limiting factors, plus the propagation delay in terms of how fast the response is. How fast your input frequency is, how fast you'll be able to capture those peaks. Just FYI, do your own math on that for your own circuit. But the point is that once this thing charges up, basically, the voltages become equal, right, between the two terminals, and the thing is happy. This diode doesn't do anything in those circumstances, so it's basically like it's absent. But, so what happens is this op amp's voltage output will actually be 0.6 volts higher than whatever the capacitor's charged to, and 0.6 volts higher than both of these terminals, because 5 volts in, 5 volts across our capacitor, 5 volts being fed back to it. The op amp's happy. So what it does is, in a conventional circuit, well, it goes to, it just goes to sleep, just kind of rests there until the signal drops below that peak. Then when it does, well, then the other one, it pegs negatively. Well, here it swings negatively, and it does that because it creates a voltage drop across this resistor. So if we had, again, this charged up to 5 volts, and it was feeding back 5 volts, but we had a sine wave that drops to negative 5 volts. Well, when it hits the negative 5 volts, this op amp still has to equalize those terminals, right? So basically, this op amp, in order for this negative 5 volts we got applied to the positive terminal to be equal, well, let's just say for this negative terminal to equal this negative 5 volts we got applied to the positive terminal, we need to apply negative 5 volts to this terminal somehow. Well, that means the output of the op amp has to swing negative 10 volts plus a diode drop, because again, normally this diode doesn't do anything in a peak situation, but in order to allow this thing to respond this way, you put that diode there, so it's got to swing 10.7 volts negative in order to drop the 10 volts across this resistor, because again it's 5 volts is what we get charged up to our capacitor, so it's got to drop you know 10 volts across this resistor to get it to minus 5 volts here. But in order to do that, this has to swing negative 10 volts, 10.7 volts. So basically there's a total of 15.7 volts dropped across the combination of this resistor and the output terminal itself to give us our minus 5 volts to balance these two terminals. So that's basically happening, but at least it's not pegging itself to the power rail, but that's what the mechanism is. These terminals, an op amp, always wants them to be equal. So, generally speaking. So, it's always trying to achieve that, and this is a quasi-linear circuit, sort of, because it can sort of achieve that. I mean, it is behaving linearly here, instead of dramatically like it does over here. So, because you can see these, waveforms that deviate from the negative 15 volts, as it goes through its cycles. So, anyway, it's a superior circuit, but, like I said, the real circuit's right here. So, so basically, yeah, that's the real circuit, and, I've got it hooked up to analog discovery, and it's not doing anything now. I got it hooked to ground just because I'm trying to see, what the voltage is, but like I said, the offset voltage is only about, it's less than a millivolt. So, with me grounding it, and I've never been able to actually successfully tune it, to try to weed out the offset voltages. But these are 380 LM3 380 or 356 op amps, JFET input op amps. But you can adjust the offset voltage with these two potentiometers. It's kind of difficult to tune. I've just never got around it because I don't know, ended up going in another direction. So I never really finished trying to get this thing to work properly. But at any rate, these offsets are still pretty good wherever I have them set. That's still pretty impressive. If I hook it up to the analog discovery, there's a bit of an offset leakage current that's always coming out of that terminal, evidently. But yeah, I'll have you note, that's what's one of the things that's very interesting about this, is that you don't really see, in all my videos, you always see all the goddamn noise I have floating around here. This is like as quiet as a mouse. So, in fact, zooming into the 50 millivolt level and so forth, I mean, it's like I said, there's just not a lot of noise on this. There's certainly some, but, it's still a relatively quiet signal under the circumstances. It's still pretty impressive. So, I got the scope set to where I can view 1 kilohertz frequencies, because that's what I was experimenting with earlier with this thing. I built this thing because I wanted to capture really fast, like as little as maybe 1 millisecond pulses, and I know I got DMMs that do that and stuff, but they don't scale it. Because what I wanted to do is hook this thing to those current shunts that you buy off Amazon, and make this so it's a peak hold detector, a fast peak hold detector that I could attach a multimeter to. So this other op amp down here is meant to be an amplifier. These things are pretty much unity gain. Your first two, these first two inputs are part of the peak hold circuit. It's all unity gain stuff. But then, they apply an amplifier to have a correction factor, so, that like you put a 50 amp shunt on it, right? But the maximum voltage on those shunts at 50 amps is supposed to be 75 millivolts. So you need a conversion factor to convert to like 75 millivolts to 500 millivolts. So, you need some gain there of, 4 point something or whatever. Let me see if I made a note of that. Well, I don't have it here, but anyway, you can do the math. Just divide 500 by 75, and that's the gain you need. So it's like 8 or something, 7 point something or something like that. I don't have my calculator handy. Let me do it. 500 divided by 75. Yeah, you need a gain of 6.66666. So the devil's gain. Anyway, the fact of the matter is that that's kind of the correction factor you need to throw in there, and then you could read out on a little multimeter. I was going to build a little multimeter into this, but I have like several shunts. It's going to hook to this. A 5 amp, 50 amp, and a 500 amp shunt. So, I wanted to make something to capture fast rise pulses, like you stick a capacitor on it or something like that, and see how fast it discharges. Under a short circuit, that kind of thing. It would be interesting being able to gain that kind of insight, because a lot of times it's kind of a guess, because you don't know what the exact ESR is and everything else. It'd be neat to be able to profile things like that. So, a fast peak hold detector attached to a shunt, might give you a good high IM meter, a peak hold high IM meter. But anyway, I think I'm going to end up going in different directions on that project. But it's still an undone project. I mean, I've got all the shunts and everything for it. I just never finished it up because I had these problems, given the fact I did the circuit wrong. At first, I couldn't figure out what was wrong with it. So I just assumed it didn't work, because by the time I designed this circuit, hell, it had been so long since I'd studied the book, I already half forgot how it worked. But definitely by the time I built it, 6 or 7 months later, after I designed it, I definitely didn't remember what the hell was going on. But I still ended up fixing it, the problem. So I still ended up tracking it down eventually. But yeah, it was confusing, and I was really in a kind of a bad state of mind at that point. But at any rate, hold on. I'll see what I can do to show you how this thing works. Yeah, when I first, before I get to some experiments here, I wanted to say that when I first did this circuit, I thought, because it had 2 rectifiers in it, like an idiot, because I wasn't as up to speed on this shit as I am now back then. This is a few years ago. I, did this design and, built it like, 2.5 years ago, something like that. But yeah, I thought because it had 2 rectifiers in it, there was a full wave peak detector, but it isn't. But doing a full wave peak detector is a little tricky, because what you've got to do, and I worked this out recently. What you got to do is you got to have a circuit like this, which is a full wave rectifier, right? Ideal rectifier. But like I said in a previous video, you'd want to use an op amp. You wouldn't want to use 741s, because if there's any offset voltage, it'll show up in the output, and the peaks will be uneven, just like I showed you in that video I did, with the simple, ideal diode. Yeah, and you don't want that, obviously, so you'd want an adjustable, like a 356 or something like that. Well, I guess a 741 you could probably do it, because it has offset nulling too, so you might be able to get away with it. This depends on what you want to do. But you'd want to make sure the peaks are of equal amplitude for a sine wave input, right? So you'd want to adjust that, but then you'd want to feed it into a circuit just like I got here, just like this one. So you'd have to have 2 independent circuits, and yeah, this does rectification too, but that's a necessary part of its process in peak holding. But the thing is this is my output amplifier, right? So if there is error introduced, again, as long as this circuit, was properly offset nulled, right, to where the peaks match, well, even if the voltages aren't exact stored in this capacitor, still, you use this circuit to adjust out any error. That's what it's meant to give you a reading on a multimeter, right? That's why it has gain, and like I said, 6.66, is our gain, But like I said, even if, the 1 millivolt error I got right now, well, at a 500 amp shunt, that's like 6.66 amps per millivolt, right? So, that's still a pretty good error. If I was looking at that and saying, wow, I got 6 amps when there's no amps flowing through it, I got it grounded, you know. Or if it's a 50 amp shunt, it's going to be 666 millivolts, will be across that resistor, would be the output. Again, ideally, but that would show up as, looking like, with 1 millivolt that we got 600 milliamps on a 50 amp shunt, or on a 5 amp shunt that we got, 66, 66 milliamps instead of 666. So, there's an error there, but because I can adjust that gain, I can actually tune that out, just by adjusting it down to offset that, to, what might be a lower reading. So, actually, I don't know, that might not actually work. Yeah, I don't know if I can tune out that offset error or not with it, but we'll find out. But at any rate, the point is that you will have errors, and I could adjust it, for at least a fixed current, having the right voltage, just by adjusting that gain. If there's a constant gain error, but still that error would probably be constant no matter what voltage. So I don't know for sure, but I'll find out. Here I wanted to show you right now. I got the terminal disconnected, so it's not hooked to ground anymore, but you can see there's a drift. Here, let me reset it. Well, let me zoom in a little bit so you can see it a little more clearly. Okay, it's 50 millivolts per division, 20 millivolts per division. So let me reset it. So, with no input, it actually has a negative drift to it. So, it's a floating input. So, who knows what it's going to do, but it actually will, start charging that capacitor negatively. So, but that's happening, partly through that diode because of the diode leakage, so, because the diode can start to charge the capacitor backwards, if it's pegged negatively, and that's why it discharges your capacitor. And again, in this circuit, it still will do that, but I mean, it has a really low discharge rate. But at any rate, it's just a great example, of what's going on. If I, hook it up to Analog Discovery's terminal, which I don't really have anything coming out of it, except it does come from an op amp, so there's going to be some offset in that op amp and everything, because I don't have that adjusted out for that, so I still got to hook to that mixer circuit, basically, that I did in a previous video. At any rate, so it's offset, it's a little dodgy, but I don't have a signal coming out of the Analog Discovery right now. I could apply a signal to it and kind of show you how it works right now. And oh, by the way, I went ahead and hooked my scope probe to the actual amplifier output. So instead of, to the raw, well, wait a minute, no, I didn't. No, it's still hooked to the raw signal right now, but I'm going to go ahead and, well, I'll leave it like that. It's easier to see right now, because I was in the process of actually doing that when I decided to start the video back up again. But, so we can apply a signal there right now, and but I got everything set too high. I need to have it the same voltages. Okay, 5 volts per division. Alright, so because this I got 5 volts per division, and that I got 5 volts per division. So basically you can see the peak waveform. So I got its amplitude set to 2 volts peak to peak, and I'm gonna lower it. Let me use this instead so it's quicker. So I'm lowering the signal. Now I'll reset it. Okay, our peak detector is detecting that peak. Now let me up the voltage. Okay, see how it follows it. So, and that's its maximum voltage there, 5 volts. So I can reset it now, and it pops right back up. So, but I reduce the sine wave amplitude and reset it, and bingo. So Anyway, that's what's going on in that terminal. Now let me go ahead and move our scope probe to our amplified output, which is set to about 5 or so, I think. Okay, so that's what that looks like, on the amplifier. Yeah, I can't really tune that offset out, like I was kind of thinking I could. So yeah, you're kind of stuck with it. You really need to get rid of that offset voltage. Now, if I was putting that into a microcontroller, then I could just offset it with the ADC, right? I could just offset it in my readings. But that's about the only practical way to do this. But that 1 millivolt, unless you can tune it down, which is going to be hard to do, but this is still pretty low noise. I mean, I got to admit, it may be possible to kind of tune that down quite a bit. But yeah, unless you can tune that offset voltage completely out, it'll be, always a bit of an error on your reading. And again, I can't really adjust it out in the output amplification because it would be different at different readings, because it'll be a constant offset. So, I can't tune it out because it's constant, But again, if I put it into CPU and then did an ADC on it, I could always eliminate that out of the readings because it is constant. Even if it was non-constant, you could do it as long as you had a profile for it. But at any rate, yeah, that's after a reset. Let's see, let's get this even lower to 600 millivolts, peak to peak. I mean, again, you really can't see it that well, but get the camera closer, okay. Resetted it, because remember, this is being amplified now, so by about 5 times or something like that, because our, output on channel 2 is 2.3 volts, but our input, is 400 millivolts, peak to peak. So it's like 200 millivolts or so. So, you can see it's multiplying by, it should maybe 10 times or so. But let me turn that sine wave off. And I guess I'm still, oh, well, no wonder I'm generating a signal. Okay. Yeah, I had my other generator on already. Let's see, I can adjust it up to 500 millivolts. It's going negative. This doesn't respond to negative peaks. Let me go ahead and reset it. Alright, so it doesn't respond to negative peaks. Like I said, our output right now is about 80 millivolts. But again, most of that's coming from that other op amp that I have this hooked to. So, and maybe the analog discovery, but definitely the other op amp. At any rate, let me go the other direction, and you can start seeing, how it amplifies down to almost 0 on the input. Okay, we're at 0 right now, and C2's output is like 97 millivolts. Like I said, I wish you could see this, but I can't find a tripod. I have one, I don't know where it is. But let me start going the other direction. Okay, so now we're, because again, that mixer I have is an inverting mixer, so, in other words, I got to put negative voltages into it to get positive voltages out of it, so that's why I'm having to tune it backwards. But you can see, how the amplified version of it, far outruns the signal itself by a constant factor, because it does have gain to it on that third op amp. So, and I reduce the signal down, because see, our output's almost pegged now. It's up to, that's up to maximum already. So, I could reset it, because again, I got this powered with plus or minus 15 volts. So, but yeah, that's as far up as it'll go. As close to the power rails it'll get. But, so let's look at a typical scenario here. Let me keep reducing it. Okay, it's 500 millivolts. That's still way too high. 10 millivolts, 20 millivolts, okay, 50 millivolts. So it's a 50 millivolt signal. We're input signal, we're getting, well, it's actually only registering as 24 millivolts. So again, that's partly due to the op amp I'm feeding it to. So I gotta, well, no, that's the peak to peak. I'm sorry. Yeah, it's 96 millivolts. So it's, it's putting out a lot more current than I would have expected on C1. Let's see, but I'd like to try to get it down to, I guess I could set the gain at a higher voltage. That'd be easier because it's, squirrely with any noise on the system. Let me try to see what it takes though. Let's see, it's distance of 40 millivolts. Okay, that's still still 88. Ah, shit. So you go to 30 millivolts. Okay, 78. We're closing in because I'm after 75 millivolts. So 28. Okay, that's about at 75 millivolts input. Our input signal is 75 millivolts now, and our output is 416. Now, if you remember, I said I was trying to tune it for since we're 75 millivolt shunts, I'm trying to tune it to, an output of 500 millivolts. So, trying to see how stable that actually is. Oh, wait a minute. Okay, had to reset it. Okay, let me hold it in for a second. All right. Yeah, 234. So, so again, I'm after 500. So let me see if I can tune this little pot on this to try to adjust that gain. Again, I'll probably end up doing this at a higher voltage. It'll probably be clearer, more precise, because this is still kind of a little dodgy in terms of how it's fluctuating. See if I can tune it. I don't know. Okay, 250, 190, 300. I just ran out of range. So that's the best I can do. Unfortunately, I didn't get myself enough pot range, depending on where the signal came out. So that's a design flaw there. So this is the best I can do, is about 300 millivolts. So it's about a gain of 4. It's about the best I can do. But let's try a higher voltage though. Go up to, instead of trying to do 20 or 75 millivolts input, I'll try to do 750 millivolts input. So let's see, I've got our input at, let's see, C1 is 250, so way below still. Okay, 50, we've overshot it. Well, no, we're still less. Let's see, 500, 600. All right, 60. All right, 71, 710 millivolts. Closing in on it. Overshot it. Still too high. That's about right, about 750 millivolts. So basically, here, we are getting a gain of 5.3. So I don't know, maybe the thing just doesn't work that well at that level, but let me adjust it down now. Oops, I guess I got to reset it. Okay. 4.9 volts. 491. No, yeah, ran out. So we're closer now, though. I mean, again, a lot of that's probably due to the error of the lower voltage, but We're almost 4.9 volts for a 750 millivolt input, so that's close to what I was after, but I didn't give myself quite enough range on this pod. Um, but I can't really. The next step is trying it at 7.5 volts, but that's not going to work. Um, so, at any rate, but we're after a gain of about 6.66, and we're really close to that. In fact, you know, pretty close. Remember, we do have that pesky offset voltage here that's going to be uniform, and that's like throwing my readings off at the lower level. The fact we got that 1 millivolt inherent built in, but it's always inherent in it, so it's got more precise when I up the voltage. Because it's still only a 1 millivolt error, but it's multiplied by the gain of our final op amp. Which is close to certainly over 6. So so it's like a 6 millivolt error in this thing because of that. So, but at any rate, so even this reading is actually higher than it probably should be. So, but again, I just didn't give myself enough adjustment range here to even come close to doing this. But let's see what happens when I put a volt into it. And let's just see it, read it directly that way. But again, I'll have to tune it though. So -1 volt. We're very close to that, 1.05 volts. So, yeah, our gain on that is 6.9 supposedly. So again, if 6.6 was ideal, but again, we don't have the exact voltage. Let's see. 998. No. 0.998. Damn it. I have to reset it now. Okay. But no, it's still too high. Okay, 1 point, about 19 millivolts off. Let's see. Yeah, it's probably about as close as we're going to get being all the discovery. So let me reset it. Okay, yeah, it's about 6.61 is the gain we got here. So it's not quite what I needed. 6.67 is the gain I needed. So I can't achieve that because I maxed my pod out. So, but anyway, it's kind of close. It's kind of close to giving me the range I was looking for. So that's encouraging. But you can see, here, let me stop the signal, and just stop the scope. So our input, I guess that's the op amp itself, having some capacitance in it or something, because our input signal is still saying it's about 1 volt for some reason. Because there's still an impedance to it. Interesting. Well, that's strange. Let me run it again. Okay, 948 millivolts was our setting. Now let me take this down to like -100 millivolts. Alright. Okay, so now it's weird how that stuck there. I mean, the output from that that mixer was still sitting there at about 1 volt even when I turned this function generator off. But so okay, so I got us down to 100 millivolts, but I'm trying to show you, if this thing holds its charge, quite well, certainly long enough to get a reading like I wanted off of it. It is diminishing, and it leaks out really slowly because again, it's still going to have leakage current going through that diode for one thing, and plus the capacitor itself is a tantalum, but it'll still have leakage current to it too. So I mean, eventually it'll draw down, but it actually takes it quite a while. surprisingly enough. Even if I charge it up to, about the power rail, I mean, it still, can take it like, 30 minutes or more to discharge, down to a signal level. So, I mean, it holds its reading quite well, long enough to, because that's the problem with a lot of, like, multimeters. You try to, like, let's say I wanted to do a short circuit test on a transformer, without blowing the breakers. Well, what you'd want to do is you'd want to have an input signal you apply to it. It's very brief, a fraction of a second, like, half a second or less, right? And then see what the short circuit current of a transformer is, because again, it's still difficult to actually determine that, right? See what kind of, what might happen to your circuit if something short circuited, right? What kind of current are you dealing with from this particular transformer? Well, you could hook it up to something like this, and you got to be able to control the transformer really quick, and that's what that other half of the circuit was meant to do that I have up here. This is a microcontroller, a PIC microcontroller based circuit that's supposed to actually control things like that, so you have a very precise window of, to work with for things that are load sensitive. If you left a transformer hooked up with an ammeter, like a high ammeter, by the time you're done with your measurement, your room would be on fire. So, because you're doing a short circuit test, right, it definitely blow your breakers on some of those transformers. Even relatively, a 200-watt transformer, can put up enough current on the, from the secondary to the primary, and to burn out your windings, and the transformer's properties would change. I mean, you just can't get a reading fast enough, especially with a clamp-on current meter, which generally are the only ones you have available. But something like this is a shunt meter, so it's a straight resistance. You can get a reading really fast with it. And if you had a good fast peak hold circuit that can do 1 millisecond or less, transients, well, then you can get a good idea of what that is. And I did have a raw input output on this thing too. That fourth op amp, I had down here was meant so you could feed it to an oscilloscope, so you can get just kind of a raw reading of, so you could, oscilloscope capture the waveform too from those 75 millivolt shunts if you wanted to. Of course, a lot of oscilloscopes don't do to 75 millivolts, so really having a 10x amplifier in there would make more sense to get it up to a better reading, given the fact that, like I said, the resolution is 75 millivolts per full range amperage. So, so if you got 5 amps, you might generate 66 microvolts, as an output per amp. So, that's, well, that's not true. That's per, yeah, but I mean, like on the high end shunt, it was 6 amps per milliamp, right? For the 500 and the 50, it would be 0.6 amps per, millivolt, that kind of thing. But my point is, with the, with the readings being that low, significant readings, 1 millivolt makes a big difference, and still that can be really hard to observe on most oscilloscopes. So it's best to have a gain of at least 10, so you can get that, instead of it being like, for example, 6 amps per millivolt, it's 6 amps per 10 millivolts. That's a lot more oscilloscope friendly. So that's what I was trying to say. But yeah, I mean, like I said, this thing, it's been sitting here, in a discharge process this whole time I've been talking. So, and it's continuing to discharge, and I can reset it. So that's its reset level. That's where it's trying to discharge to. So, it holds its charge pretty well. This little tantalum capacitor I had in my junk box is 10 microfarad. But again, that will limit its response range too, like I said, in a lot of practical circuits like this, you may want a smaller capacitor so that it responds faster. So, because it takes time to charge a capacitor, even with a low impedance op amp. Unless you had a high current op amp, you could charge it faster. If it gets too fast, you might have some overshoot though, and you wouldn't want that. But at any rate, yeah, I wanted to add too, a really good book to get, if you're, serious about this shit, is get the Circuit Designer's Companion by Tim Williams. You can get them off thrift books, for pretty cheap. The one I got's like from the early 90s, but it's still really, really valuable. Really, really good insight. And still quite relevant to things today. But he has a newer edition that was from 2006, and those I think are still available in thrift books. You can probably get them off Amazon too. But I was going to say too, you might be wondering why I don't try to trim out the offset on this circuit, because it's actually rather difficult. Because okay, with the output off amp, I could short circuit by pushing the switch in and calibrate it, but of course you can see that when I do that, that creates a big load on your first op amp, so I'd have to remove it from the circuit, which I can because it's because it's socketed. So I mean, I could remove the first one and then calibrate the second one, offset wise. And even with the switch pushed in, I mean, technically it's sort of part of the error voltage, but anyway, that short circuits at the ground. Then I could try to calibrate it, but then I'd have to put the first chip back in, and the only way to calibrate it, to try to, offset null it, is to like desolder stuff. I'd have to take the capacitor out, put a resistor and across it to ground, or maybe remove the diode. But I definitely have to take the second op amp out to do that, because I don't want this feeding current into this one, and plus, even if I took the first op amp out, I guess it would be fine if I took the first op amp out. I don't think it's going to hurt it. Yeah, that would be fine. Yeah, I could take the first op amp, because its output will have a load of 10K across it, still going to ground through 2 diode drops. But just trying to think, that still might be a problem, because I am trying to, offset null it, because ideally, you want to certainly put like a, just a flat out resistive load there, but having those 2 elements in there, that may not work. So again, I'm just not really sure, without the soldering components, how to even for sure calibrate this, but definitely calibrate this. I don't know how to offset null it without desoldering a bunch of shit. So it's real tricky to do, and I haven't quite figured out a good procedure with it. But this version of the project's a dead project anyway, so I'm not really worried about it. But I've always been kind of curious to explore this in greater depth, so I'm taking the opportunity to do that, for peak hold circuits in general. But if I did this in the future, I'd do it microprocessor based, and then I wouldn't even need a peak hold circuit. So, this kind of becomes irrelevant for that, but it may be relevant for something else. But at any rate, that's why I haven't calibrated it better, because it's difficult to do, so, without desoldering a bunch of shit. So I don't know. Imagine if you have to recalibrate it, and like I said, if I go removing chips, like if I remove this chip after calibrating it, so that I could calibrate this one, even with desoldering components, well, I might have to recalibrate it, because, even galvanic differences, from taking it out of the socket and reinserting it, may create different contact parameters, than we originally had. So I don't know how much that might throw the error off, especially if there are dissimilar metals between the chip leads, particularly with the smoke damage these things have, and the actual socket metal. I mean, if those are different materials, even slightly, that can generate an offset voltage too. So, but that may change if I remove it and then reinsert it. I don't know. Then I'd have to go through a complicated process all over again. So that's something to keep in mind. It might be better to calibrate these things as you build them, and cross your fingers that they hold their calibration. But if you didn't have to tweak it much, you might be able to, once you got it basically calibrated, you still may be able to make fine adjustments without having to go through that process, as long as they're just slight offsets from whatever your original 0 point was. So, but any rate, that's why I'm kind of working with it uncalibrated. So, because that was one of the other things that I figured several years ago was going to be really difficult to do, is to calibrate this out. Um, Alright, so I've gone ahead and hooked it up to my lowest end shunt. This is a 5 amp shunt. And you can see right now the C1, the yellow trace, which you can't see right now, it's buried, but it's at 3.5 millivolts with the power supply disconnected. Let me zero it real quick. So yeah, I just zeroed it. Still, the output's 4.45, so that's, just under a millivolt error. Then again, I can't tune out, but let me hook the power supply lead back up so you can see what happens. I disconnected it because there's an offset voltage coming out of my power supply of another 4 millivolts or 4 or 5 millivolts. So I was trying to figure out where that was coming from, so I unplugged it. But yeah, it's so that's a baseline. Again, I can try to re-zero it, but it buoys back up to where it is, where you can see it. Okay, but yeah, I will try to apply some current to this thing. I got it set to, and this is interesting because, I got my current, on my power supply, and this is the power supply I'm testing it with. Right there, I've got the current set to, limited to 2.3 amps, and I pump the voltage up to 19 volts. Because, of a constant current source power supply, you think, well, when you hook something up to it, its current will be no more than 2.3 amps. And, the chances are pretty good it'll actually, there's a peak that comes with it. And you'll see that. But let me go ahead and turn it down to, like, just for calibration, so we get an idea to it. Well, tune it to 1 amp and let's see what happens at 20 volts. Damn it. Okay. Alright, so, and this discharges fast because these are small voltages, relatively speaking. But let me turn it on just briefly. Alright, so that's what we captured, and like I said, our C2, our output has actually jumped to, like, with 1 amp going through it, it's jumped to, 84, 85 milliamps, or millivolts. So we know, 84 millivolts, is pretty much equal to 1 amp here. But that's supposed to be full range of this thing. But then again, we're going through our amplifier, don't forget. So we're not seeing what the, no, actually we are seeing what the raw output is. So that actually is the raw output right now, because I don't actually have it hooked to the amplifier like I did earlier. So yeah, I mean, it's just with 1 amp of circuit, a current, it's jumped from 8 milliamps, up to 57 milliamps, apparently. Let me reset it again to hold it in for a second, because there might be some, dielectric absorption involved here, so let me hold it in for a second. I mean, having it at higher voltages before, so, Alright, so let loose, it's 8 or 9, so we got to subtract, 9 milliamps, or millivolts from that reading. Okay, so it's 58 millivolts. Its input is reading 23 millivolts, so there's quite an offset there. So, that's like 61 millivolts, about 60, so it's like 50 millivolts, for a 23 millivolt signal, which makes me wonder, how good, because again, that could be an error in analog discovery too. Again, I should be using a fluke, or something for these kinds of tests, but, I'm just doing it for analog discovery for shits and giggles. But yeah, so like I said, about 50 millivolts, per amp right now, which again, it shouldn't be that. Let's up it down to, up it to 2 amps and see what the difference is. Alright, still it's, its output's still only 61 millivolts. Now it's, pretty much the same damn thing. So, our input's 40 millivolts. So, yeah, that's not too encouraging. I turned the voltage down. Now it's performing a little better than it did at higher voltage. So I turned the voltage down to 9 volts. Let me reset it. Okay, yeah, now we're getting a better response. So that's probably, the power supply is, it's going from 20, because again, the shunt's supposed to be 75 millivolts full range, to the best of my knowledge. So maybe it's not. Maybe it's a higher range. I'm pretty sure these are all 75 millivolts. So like I said, I got to evaluate whether analog discoveries have something to do with this. Because at zero current, it's at 8 millivolts. All right. So, 2 amps are at 40 millivolts. So it's like 30 millivolts for 2 amps. And again, the range on this thing is 5 amps. This power supply can do 5 amps at this voltage level, so I'll turn up to 5 amps and let's see what that does. Oh, it blows up my power supply. Let me reset it. Okay, it's 104 millivolts at 5 amps, so that's not too out of whack, and it's 1.3 millivolts output, 123 millivolts. 130 millivolts output, so it's really 120. So it's 120 millivolts, over 5 amps, is what it's putting out, and that's versus 8. Well, it's 120 millivolts, minus 8, so it's 120 millivolts over 5 amps, assuming it was 5 amps, but that's not out of the question, because again, our shunt, went from 8 millivolts or 8 or 9 millivolts, to 104, so that's about 95 millivolts. So the shunt's out of calibration to that extent. So the shunt's cool to the touch. There might be some warm-up time or something, because the shunt resistance will likely increase a bit with current, and maybe that's how they size these shunts, rated for average current. That wouldn't surprise me, In other words, it's 5 amps, the shunt's going to heat up a little bit, and that's going to change the resistance a little bit, and adjust those properties. It might be a little more accurate. I don't know. You'd think the voltage would increase, though. So I don't know. So I'm not really sure how they calibrated that. But at any rate, for our purposes, we know that it's going from 8 millivolts, right? Let me reset it again. It's going from 8-ish millivolts on C2 to 128, so it's 120 millivolts difference. All right, so 120 millivolts divided by 5 amps is about 24 millivolts per amp. So in theory, therefore, if we jumped it back down to 2 amps, it should be 58 millivolts should be our reading. Let me reset it. But, our reading is, let me do that again. It might have some dielectric absorption. Let's see. Okay, Okay, it's reading like 70 milliamps instead, so it should be reading 48, so it's like 10 milliamps non-linear or something, so that's interesting. So, so again, that's not the reading I was expecting, but let's see what the shunt reading is at 2 amps. It's, 44 millivolts from 8, so it's like 30 millivolts, which divided by 2 would be at 15 millivolts, so it seems like the shunt may not be linear either, but it may be analog discovery too. I mean, I can't rule that out because, again, I should be using better equipment for something like this. Let me pump it up to 3 amps. Because according to our calculation, 3 amps should produce about an 80 millivolt change, assuming it's repeatability is there, but it depends on how precise this actually is. Okay, we're at our starting point. Okay. So it's 64 millivolts. Part of it could be this power supply too, because this power supply, is not going to be all that precise as well. So that could be a large part of this as well, because it's making different noises depending on the current, obviously. So, I can't rule that out, without having an accurate current source. Let's see. So yeah, I can't really count on it, right? So, without more precise current. So I would have to rig that up. But you kind of see the principle here. But let's go ahead and, for shits and giggles, because yeah, I'm going to have to abandon that. That's just imprecise enough. Because like I said, there's a good chance it's the power supply, more likely the analog discovery at this point that's causing the issue. So let me, discharge this thing. And again, it's got, I got the current still turned on. I'll turn it off. See, it's not making noise anymore, so I wouldn't know that I had it turned on, the power supply. Okay, so, C2. Because that's the thing about these capacitors. They have dielectric absorption, so, you got to leave them discharged for quite a while, but the higher the voltage you charge it up to, the quicker it takes them to discharge. But plus this thing, I am taking it through the output amp now, which is, about 6 times amplification. So we're going to have a different baseline than we did before, because it's, about 5 times the offset. Okay, so, 20 millivolts is our output. Now, let's recalibrate, at least we'll get some gain out of it this time. Because I guarantee you this power supply is not going to be accurate, in terms of the current, short circuit currents it's putting out. So, alright, so we're at, 1 amp. Turn it off. I'm about to show you something interesting here, and one of the reasons I wanted to build something like this, because it still is effectively doing that. Trying to interpret what we got going on here first, just for a second. Okay, so let's put 1 amp through it, and okay, so it jumped up to about 300 millivolts on the output at 1 amp, but I don't know if you can see it, but it's drifting downwards. So what you saw there is a peak current that was applied to it temporarily, I believe. Because our input is staying steady. C1 is actually 25, 23 millivolts or so, but our C2, is actually drifting downwards, and it should drift down to about 100 or so because again, these are very low voltages, but it still, holds its charge, quite well. Okay, it looks like it's stopped now. So what you saw there, it stopped at 100, but it went up to 300 millivolts on our output, from our amplifier. So that means instead of putting 1 amp out or whatever it's actually putting out right now, it was putting out 3 times that amount of current. But it was very brief, but this caught it, because that's what happens when you take a power supply that's set to a constant current and you hook it to a circuit. There will be a current surge at the very first, and it don't expect it to be just like 1 amp if you got it set to 1 amp like this. There's evidence to suggest this was 3 times that. So and it finished off at 100 millivolts, so it's really an 80 millivolt difference we're setting at 1 amp. So so just keep that in mind. But now let's try upping the current to, so remember 100 millivolts is our baseline, and 300 is what it popped up to. So let's want to do this briefly. Okay, now let me reset it. Alright. Okay, so it popped up to 500 millivolts. Alright, and it's drifting down, and this is at 3 amps. But I can actually just reset it. Okay, and that's going to be our final point. I don't have to sit there and wait for it to discharge. Okay, so it's settled at 300 millivolts, which is, I got it set to 3 amps, so that's 3 times the current, so that's, you take the 20 millivolt offset out, that's, about 3 times. So that's a little more than that, but again, this isn't going to be that precise. But you saw it jumped up to 5 at first, right, when I first turned it on. I'll turn it off. Let the, it's got a capacitor inside of it. It'll just charge quickly. Let me turn it on. See how much it jumped? So, yeah, it even jumped higher that time. So, jumped up to 670. So it's still over double the current. That means it ostensibly put out like 6.7 amps, compared to the 3 amps we're thinking we're going to get out of it. Now let me briefly turn it up to 5 amps. It seems to do this more on low voltage than high voltage, interestingly enough. Alright, so 5 amps, got us up to, that's much better regular. It's still 800. But the power supply is more struggling. I can actually hear it like crazy screaming. So anyway, that pretty much, it's kind of a little treatment, of making an ammeter kind of similar to this. Again, there's some bugs to work out for sure, but in principle, it basically works. But again, if I had a more precise power supply, more precise current source, I could probably do this. But at higher amperages, it's better, to use one of my higher amperage shunts, with a high amp power supply, which I do have some of those. But those, I can kind of measure with other meters more easily than this. I mean, I actually could hook an ammeter up to this thing, actually, and see what the actual current is, I suppose. But again, I don't want to get that involved with it. But, here's an example of my 500 amp shunt. So you can see how beefy that son of a bitch is. And then, of course, the 50 amp shunt's just one of those normal ones you get with Amazon meters. But anyway, it shows you the principle, one way to use things like this. So I know it's a long video, but I wanted to cover it even for my own benefit, so I can come back and see what my test results are. I mean, like I said, I wish I could have recorded the test results of my testing it 2.5 years ago, so I could have come back and reviewed that. I wouldn't have to do as much work all over again trying to recreate whatever it was I did. So but at any rate, that should about wrap it up. So cheers, unless I think of something else before I stop the video for sure. But yeah, there is something. But of course, you could put the output of one of these shunts across an oscilloscope and capture it that way if you have one. But sometimes that's a pain in the ass. You got your oscilloscope hooked to other shit, and it's just nice having an independent little piece of test kit. And like I said, I could have put an ammeter across it like my Fluke, which I think does have a peak hold current function. I'm not sure about that, but I know it does on voltage. But you're measuring voltage, so that would work fine. So I could just use it for voltage. But I hardly ever use ammeters, DMMs for ammeters because you just blow fuses all the goddamn time. I just got sick of it, so I hardly ever use them for that. But here you're measuring voltage across the shunt. You can do that, and you could probably get an accurate reading, but it just depends on your fast response. Like that little high current spike you saw off that power supply. I don't know if I could have caught that on a DMM. I don't know how fast it is, but putting on an oscilloscope is what you'd want to do. Even with this, if you wanted to look at the actual event, that's why I had an oscilloscope output on this. But really, I should have put an amplifier on that if I wanted to use it for an oscilloscope, because of what I was talking about scopes not being really great with low voltages. They can resolve voltages, average price oscilloscopes, that amateurs can afford, 2 or 5 millivolts or so. This is the noise floor on them typically, with an actual probe connected to it that, mere mortals can afford. But some of those scopes just null their noise out when they don't have a signal attached to it, like this one I have over here I think does that. I think it cheats a little bit. I don't think you can see the actual true noise floor on it just by disconnecting the probes. But even my good analog scope, can resolve to about 2 millivolts. But you're not going to do much better than that. That's why having some kind of amplifier on is a good idea. So go fuck yourself, you fucking cocksuckers. Fucking adware, something bullshit. But that's how you would normally do it. And then of course you could measure waveforms directly from these shunts that way. With an oscilloscope, you wouldn't technically need something like this. But the thing is that it made sense to build this anyway because of the fact that, of course, back when I built this, I didn't have as good of equipment as I got now, for one. But the and my equipment's not high dollar, but it's way the fuck better than what I had. Again, it's you still need to have control of the power source a lot of times. So I needed to build a circuit anyway just to control whatever it is you're trying to measure, so you can do it very briefly. So so with that being said and everything, it makes sense to just want a meter like this, especially one that can do some high voltages. But yeah, I can take any of these shunts and hook an amplifier to it for sure. At least a 10x, and probably a cascaded 10x to give 100 gain, and good frequency response. And then, you could check it out on a scope, but you want to use precision components to make sure you got 10x if you want to actually measure it. And that's the other reason, is that traditionally, especially the scopes I used to have, generally, the measurement wasn't going to be too accurate. Still isn't, even with most scopes. So if you're trying to actually measure the voltage and everything, you can get a good estimate though off the gradical and everything, and maybe using cursors and stuff, will give you a good idea. But again, what I used to have, really, that didn't work so well. So it certainly made sense to have something like this. But at any rate, a circuit like this, I'd rather do with a microcontroller as part of some other project perhaps. Because then you can actually record your data more conveniently. But the reason I didn't want to use an oscilloscope mostly is because, you're still going to have to frickin' multiply it, by some factor if you just read it right from the shunt. So unless you set up an amplifier that you can adjust, you can calibrate, like I was talking about doing, trying to hit, 0.5 volts, for, a 75 millivolts input, the 6.66. So unless you have a gain of at least that, you're still going to have to do a conversion on it, and that's a pain in the ass. So, so again, with this like analog discovery, I could actually just make a math function to do that. I wouldn't need to interpret it. But with the equipment I had back then, no, I'd have to get out the damn calculator every time, and I'll probably make mistakes, and so that's another reason I wanted to build an instrument like this. So because I can read it off a multimeter if it's fast enough, but you're still going to get the damn calculator out, and then remember what all the calibration settings were, for calibrating out the inaccuracies in the shunt itself and all that bullshit. I mean, this allows you to kind of do a lot of that automatically, but a CPU version would be even better. So anyway, cheers. Okay, one last thing I'd like to say, is about this power supply. I can calibrate this because it's actually tunable down to the milliamps. So, damn reflections. But see, I can tune it down to the milliamps. So I could hook up an ammeter to it, like a fluke or something like that, and then tune it to get the short circuit current I want out of it, and then make note of that, on a list and crap like that, so that I can go in and and then run more precise tests on this, to calibrate it. That's one way I can go about it. There's a number of different ways I can go about it, but for this video, I'm not going to get that involved in the circuit. Again, it's just for curiosity more than anything, because it's like unfinished business, that I never was able to conduct because I didn't have the equipment to conduct it, 2 or 3 years ago. But my point is, it can be done. And of course, if this were microprocessor based, it would be easy for me to build those calibrations into the processor itself, so it makes those adjustments. Because I could actually make a calibration table in a CPU, that actually deals with things like that. For this particular power supply, I mean, it can actually make that a special profile for this power supply. Here's an adjustment. When I have it set to 1 amp, but this is what it really is. That kind of thing. So, things like that can be done with CPUs that aren't so easy to do with a flat-out analog circuit like I was trying to build. But again, hooked to a little DMM, which I was going to build into this, a cheap DMM I got from Harbor Freight for like $4. Would be fine for something like this, because they're actually, those little cheap DMMs from them are actually based on a really good chip. If you ever open them up, they're actually all through hole inside, believe it or not. They're based on a, or at least they used to be, based on an actual chip that I actually have like 3 or 4 of in stock. It's like a 40-pin IC that's a voltage regulator. It's actually well regarded out there in the literature. It's like a 7107 or something like that. IPL 71, forgot what it is, but at any rate, I actually had a design based on one of those, but I didn't do the circuit board right. It wasn't routed deep enough, and I didn't realize it, so it's basically just a big short circuit, so I never built it. But it actually will directly drive LED displays, so you can actually make your own meter with it, your own DMM with it, with a few extra parts. So it's actually fairly precise, and it'll do positive and negative voltage readings, and again, you can put the appropriate scales in it, and I think it can go up to like 20 volts or something by default, something like that. But at any rate, I digress. But the point is, I just wanted to point that out, that, if you're dealing with wanting a precise standard, there's a lot of ways you could do it. I mean, you could take a car battery, like one of those, and stick some power resistors on it, and, try to tune, or, like that big potentiometer I have, over there, which you can kind of see it laying right there, that I think that's it. That I've used in other videos anyway. I don't think that's it. No, it's right over there. Right there. But, I've used that in other videos. You could take something like that and stick it on there, because that can handle, a couple of amps. So, that could be a way of calibrating like a car battery or something like that, with a power resistor. That, you put a meter across it, measure the voltage, that kind of thing, if you didn't want to hook your DMM directly up to it for some reason. But at any rate, the point is, there's a lot of ways to go about it. So, but yeah, I just wanted to, kind of cover some of these issues and mentioned that before I left. So that's it. I'm wrapping the video. Cheers.